let's start. I'll ask you to look at the sample problem on the bottom of page 404 and have a look at the practice problem. What you just picked up, the first couple pages of this is just information, okay? Ideally, we want to get through this and this, okay? The rest of it is actually a worksheet. I don't know if I'm going to check the worksheet, but I will go through some of these on the overhead with you, just to give you an idea how each is done. The families of organic compounds we're going to talk about are kind of here. This isn't a worksheet, this is just a summary page. So we're talking about alkanes, then we're going to do cycloalkanes, then alkenes, then alkynes, aromatics. That will be 8.1. And ideally at the end of 8.1, we're going to try to do that. Then we're going to do what's called functional groups, which is the other families of organic compounds. So haloalkanes means we stick a halogen onto an alkane. Then we have alcohols, ethers, amines, aldehydes, ketones, ester, amides, carboxylic acid. Maybe not in that order, but we're going to try to get as many of those done as we can as well. For the most part, most of them you won't be expected to know the naming protocol, but I'll probably go through it anyway. What I'm not going to do is go as fast as I can just to guarantee finishing chapter 8, and then expect you to write a final exam on stuff that I rushed through. The fact that we're only scratching the surface of organic chem, even if we finish chapter 8 or not, means I'm probably going to opt for trying to make sure you understand what we do cover, even if we don't get to every single item in 8.1 through 8.3 or 4. I wish my computer worked. I will maybe go down and talk to Mr. Mesa and have him come and see if we can fix it. But if you look at the practice problems on page 405, it says name the following. The protocol you follow to name the following is identify the longest continuous chain. What isn't part of the chain is a group. Then you number the carbons of the longest chain such that the group or groups gets the lowest number or combination of numbers. So if you look at the first one, 1A, what's the longest chain you can get there?
5.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, 5. So what? That means the word ends in what?
Ane.
Which end?
Pentane.
Pentane. So that's the protocol you start with. Find the longest chain, that's what the word ends with. Usually what I would do is enclose the longest chain in like a rectangle. So I wish Meg would put lines horizontally, just like she does vertically. So CH3, CH3. So 1, 2, 3, 4. 1, 2. Am I missing one?
So this is like
1, 2, 3, 4.
the end of a chain, right? Hydrogen. CH3, CH3. So that's like the ends here. And then if it were C2, is it like? And then if this was connected to another carbon, this can only be like
computer working becomes immediately obvious. So, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Whether you go that way or that way makes no difference in terms of the name. So, circle the groups. What are each one of those groups called? What is a CH3 called?
Methyl.
So you know it ends in pentane.
Because there's 3 trimethyl.
You know that
Yeah,
there
you
are
got it.
3 methyls on it. Now you simply have to decide which side you number from. If you number that way, 1, 2, 3, 4, 5,
It doesn't.
you've got a methyl on carbon 2, 3, and 4. If you number this way, you also have a methyl on 2, 3, and 4. Meaning it doesn't matter which side you start numbering from. When you write the name, you give a number each time a methyl is on a carbon, even if it's on the same carbon. So you would call this 2, 3, 4, commas between numbers, hyphens between numbers and letters. And you don't just say methyl pentane, there's 3 of them. So 2, 3, 4,
Yeah, you got it, bro.
trimethyl, and then that's one word, okay? Now, if you look at the next one, it does make a difference from which side you start numbering. The next one is also a pentane. But if you number the carbons right to left, you have 2, 4, 4 trimethyl. If you number it left to right, you have 2, 2, 4, which is less. So the next one is 2, 2, 4 trimethylpentane. And May gave you each, because in the first it didn't matter from which side you numbered, in the second one it did. And if you had done this, let's say instead of going that as part of your longest chain, you did this, it wouldn't make any difference in terms of the name. It's still 2, 3, 4 trimethyl, okay? Drawing from a name is easier than naming from a drawing. When you're naming from a drawing, you gotta decide what the longest chain is. You've gotta remember what the groups are called. You've gotta decide from which side you start numbering. None of that's necessary when you're given a name. You assume the name is constructed properly. So, for number 2, I have to add something that May doesn't put in the book. We've talked about methyl, so there's our longest chain. This is a methyl group. I don't usually write CHHH when it's a group, I usually write it like that, so that's methyl. Let's say that we have this, CH2, CH3, that's ethyl, ETHYL. May gives you a propyl in number 2. That's not really specific enough. So let's say there's our longest chain, and again, whatever is a group isn't part of the longest chain. So there's a carbon in the longest chain. If we put 3 carbons on that longest chain as a group, May just calls that propyl. It's propyl, but calling it propyl isn't enough. We got 3 carbons and 7 hydrogens. If that was the only way that 3 carbons and 7 hydrogens could be connected to a chain, then propyl would be fine, but it's not. Here's another way. So instead of putting that carbon on the longest chain, I could attach that one to the longest chain, in which case I get this. And that's called isopropyl. This is called N-propyl. N-propyl means short for normal in a row. Iso, that prefix means kind of balanced, so this is isopropyl. So when Meg uses propyl, she means this. It's just that she should probably specify. I'm not gonna go into any more than a 3-carbon alkyl group. So I'm not gonna talk about butyl, because when you go to butyl, there's even more. There's N, there's sec, there's iso, and there's tert. We're just gonna stop at 3. Yep.
How come the hydrogen goes to like the other one to make it H3? Because like before it was CH2, CH2.
Instead of CH2?
Yeah.
Okay, look at how many bonds this carbon has. How many bonds can each carbon have?
3,
Four.
4.
Doesn't that have 4?
Oh, 1, 2, 3.
I can't put CH2 there because then it has 5. 1, 2, 3, CH2 would make it 5. So, yeah, that's, if I attach this to the chain, then that carbon is going on the chain, which means 1, 2, 3, 4. Or if you want to do it, that, okay? So if that's how it goes on the chain, I have this, that's isopropyl, okay? If I expect you to draw from a name, I won't just say propyl like Meg does. I would say iso or N. And so those are the alkyl groups I want you to know. Methyl, ethyl, N-propyl, and isopropyl, all right? So let's look at number 2. In the same way that when you're naming from a diagram, you find out what the word ends with by finding the longest chain. When you're drawing from a name, go to the end of the word. The end of this word is octane, which means put 8 carbons in a row. It ends in ANE, so all the carbons are stuck together with single bonds. Now, is the molecule really going to be straight? No. You could draw it all bent and stuff if you got a death wish, but just do it in a straight line, okay? We're not trying to make this look 3D. 1, 2, 3, 4, 5, 6, 7, 8. And make sure, again, because it ends in A, that every carbon has 4 bonds. Now, Meg in the question says, draw condensed. Never start with condensed, because you're going to overbond the carbon, okay? Just start with the carbon. Then, you assume the name is correct. So when you have more than one group, and they're different groups, you always name them alphabetically. You don't name them in the order of the carbon they appear from. You don't have to decide which side you start numbering from. You could start from the right and call that carbon 1, or start from the left. It doesn't matter, because the name's correct. So, if we start from left to right, on carbon 4, we have an ethyl. 1, 2, 3, 4. Whether you put the ethyl up or down makes no difference, so let's put the ethyl up here. Okay? Then you have dimethyl. Notice the di, the D doesn't put it before the E. It's the methyl, not the dimethyl. So you've got methyls on carbons 2 and 3. 1, 2. Let's put a methyl there. Let's put another methyl here. Up or down doesn't matter. And then the next one is 5-propyl, but assume she means 5N-propyl. So 1, 2, 3, 4, 5. So here's N-propyl. 3 carbons in a row. And again, the N stands for row. Those are the groups. Now you're not done yet. You're just done with the groups. You have to now finish by putting hydrogens at the end of every one of these lines. So the hydrogens are the things you put in after everything else has been taken care of. And if you want, in your book, if you do this, and this, and this, and this, and this, you can kind of figure out how you got to that. Or even if you want to do this, 1, 2, 3, 4, 5, 6, 7, 8. Now, when you look at this in 3 weeks, you'll know that's exactly makes sense based on what I was asked to draw. The one underneath it is even easier. 3, 4, 4, 5 tetramethyl. Tetramethyl what? Decane. So for the next one, draw 10 carbons in a row. Then start counting from the left if that's what you normally do. Put a methyl on carbon 3, 2 methyls on carbon 4, one up, one down, 1 methyl on carbon 5, and then finish by adding all the hydrogens. Okay? Yeah,
How do we know which branch to name first?
alphabetically.
Okay.
So E is named before M, which is named before P.
Okay.
Okay? Yeah. And if you look, by the way, on this page, notice that it says, the first page A, which says alkanes. Here's the steps. Number the longest parent chain so that the branches have the lowest possible numbers. A prefix is used to indicate 2 or more identical branches, like dimethyl or trimethyl. If there are several branches, name them in alphabetical order. So some of this is a little hard to read based on the photocopying. However,
You think?
longest chain is what?
3.
3.
You can't see that because it's on the handout. That's the whole point. So the word ends with what?
Aiden.
Methane. Or
Three carbon
propane. Sorry,
alkane?
propane.
Propane. So
And then
identify the longest chain like a little box. Circle a group. So what's that group called?
Methylpropane.
Methyl.
methyl.
So what's the name of the compound?
Methylpropane.
Good, methylpropane. You don't need a number. Why don't you need a number?
There's no other place
Because
it
if
could
it's
be.
anywhere other than on the second carbon, it isn't propane. The only time you need a number is if there's a choice. Because there's only one way to build methylpropane, you don't need to say 2-methylpropane. You can't have 1-methylpropane. What would it be if it was 1-methylpropane? What would that be? Would that be 1-methylpropane? It'd be butane, wouldn't it? Now the
Yeah.
chain would be 4. I'm mentioning this because Meg gets it wrong twice. Actually, 3 times. Okay? But we'll get there. So that one's easy, methylpropane. No hyphen, no numbers, just methylpropane. This one you do need a number. The longest chain is 5.
4-methylpentane.
Whether you go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, doesn't change the name. Once again, we have a methyl group. The word ends with pentane. But you're not gonna call it 1, 2, 3, 4-methylpentane, you're gonna call it 2-methylpentane. Because you number the carbons of the chain starting from the side nearest the group. In other words,
See, it's
you
pattern
want that
recognition.
group to get the smallest number,
You got it right.
or
Yeah.
groups to get the smallest combination of numbers. This one, longest chain, 1, 2, 3, 4, 5, 6. So let's go around this, okay? So the word ends with what?
Hexane.
Hexane. That's a group. If you go 1, 2, 3, 4, 5, 6, then that methyl's on carbon 4. But if you number bottom to top, that methyl is on carbon 3. So 3-methylhexane. And if you do this in pencil on the worksheet and go 1, 2, 3, 4, 5, 6. Again, when you look at it in a couple of weeks, you're gonna see exactly where that came from. 3-methylhexane, right? What's the name of that one?
Dimethylpropane.
It's octane, isn't
Dimethylpropane.
Louder?
Dimethylpropane.
Dimethylpropane, no number.
'Cause
You
there's
can't
2 methyl
put 2
branches.
methyls on a propane anywhere but the middle carbon. So it's not 2,2-dimethylpropane,
Okay, what the hell?
it's just dimethylpropane. Meg gets that one wrong too, okay? Notice we draw it like it's a flat cross, but it isn't. You can clearly see around that central carbon, we have a tetrahedral arrangement. Every carbon is AX4, okay? Methylpropane.
Why is it?
This one's a little
3,
tricky.
4, 5, 6, 7.
Now wish I could make it bigger, but I can't.
Octane.
And it's a little hard to read too. Can you guys see that carbon is CH3? Can you see that?
Yeah.
Which means that this carbon can't be stuck to that one.
Yeah.
Because if that's already CH3, then that means that carbon has 4 bonds, okay? So the longest chain, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6,
It's
7,
gonna
8.
be for
The longest chain looks like this 8, okay? There.
5.
Now, will it always be in a straight line? No, but here it is. And let's circle the groups.
5, I think.
There's a group there.
5.
This should kind of be over this way. That is stuck to that carbon, okay? So that group is stuck to this. That group is stuck to that. This group is also stuck to that. And that group is stuck to this carbon, okay? So the longest chain is 8, so the word ends with
Octane.
octane, correct. Now let's identify the groups. That's an ethyl, and that's an ethyl. That's a methyl, and what's that?
Propyl.
Propyl.
N-propyl.
And propyl.
Okay,
Oh.
straight line, N for normal, okay? So, if we number this way, 1, 2, 3, 4, 5, 5, 6. If we number left to right, 1, 2,
Assume
3,
the answer is yes, but
4,
I'm gonna ask
5,
that.
6. We have something on carbon 4. We have 2 things on carbon 5.
If you go for the other way, it's just
And we have 1 thing on carbon 6. So that adds to 20. 1, 2, 3, 4, 5, 5, 6. If we number right to left, 1, 2, 3, 4, 4, 5. So if we number right to left, we have 3, carbon 1, 2, 3, 4, 4, 5. And obviously that is less than this. This is 20, this is 8,
Shit.
and 8 is 16. So we're gonna number this way, okay? So carbon 1, 2, 3, 4, 5, 6, 7, 8. Now we just have to name them alphabetically. So we've got an ethyl here and here. E comes before M or P. So, we'll do it over here because we're running out of room.
Is that right? 5.
So we've got, we know it ends in octane. We've got an ethyl on carbon 3 and 4. So you go 3, 4 hyphen diethyl. Then we've got a methyl on carbon 1, 2, 3, 4. Hyphens between numbers and letters, so 4 hyphen methyl. And then we've got 1, 2, 3, 4, 5, and N-propyl on carbon 5. And here we have a hyphen between the N and the propyl. We gotta put 5 in there. 5 in the propyl. And then after the L in propyl, it's just one word. Propyl.
There's an N.
Yeah.
Since you said that it needs to be in alphabetical order, does that,
E-M-P, it doesn't
it
include
doesn't
this.
include, okay.
Okay, no, it doesn't. Like for, let's say we had triethyl, it would still be ethyl, okay? Now, someone walking in the room looking at that and go, gee, that looks hard. It's not hard, it's very systematic. And that's the point. That can only be built one way. We can draw it a bunch of different ways, but that specifies precisely all the atoms and all the bonds and all the groups, all right? Now, I'm gonna stop there because, for now anyway, because this one is not a hydrocarbon. Notice it's got a chlorine here and here, but we could do that one. That is a hydrocarbon. What's that one?
Which one?
1, 2, 3, 4, 5.
You name it, and then when you're done, put your hand up and I'll see if you're right.
7 or 8.
So
That one's actually pretty easy, guys.
2-ethyl,
6.
2-ethyl,
What's a protocol? Longest chain, that's what the word ends with. All the bonds are single, so it's gonna end in ane. The longest chain is how many?
pentane, pentane.
Hex.
Longest chain is not 5.
Hexane.
Is
You
it
can go
X?
like up like that.
Oh, you're
1, 2,
right. My
3,
bad.
4, 5,
Yeah.
6.
I forgot that's a thing.
It's 6, so it ends in hexane.
Hexane and then
Here's the longest chain. Sometimes it's in a straight line, sometimes it isn't.
I hate it.
1, 2, 3, 4,
Chemistry
You
student.
get a number from
Chemistry.
that way,
1, 2, 3,
3 to 3
So 3.
dimethylhexane. Okay?
3.
3 comma 3 hyphen, and then one word, dimethylhexane.
So dumb.
It's like
I've noticed, marking some of your tests earlier in the year, that some of you have even worse writing than me. The spelling kind of matters here, okay? As you're gonna see, I have to be able to tell the difference between an ANE and an ENE or a YNE, because they're all different. Okay? Notice what we're doing down here. Here's the other thing. You draw from a name. That one's easy. Now here they say propyl, assume that's N, but let's go with this. That's your first step. Go to the end of the word.
9.
9.
Like 9 carbons in a row.
Oh boy.
1, 2, 3, 4, 5, 6, 7, 8, 9.
3, 6.
It ends in ANE, so every carbon is connected to the maximum number of atoms it can be. That's why we call it saturated.
3, 3, 6.
Now, what else is there? Well, all we've got is methyls. And they're on 2 on carbon 3 and 1 on carbon 6. You could number this way if you want, or number that way. You don't have to draw the chain straight. You could draw it all crooked, but why would you? Why make it difficult? Just draw it straight. And then we've got 3,3,6 trimethyl. 1, 2, 3, put a methyl here, and a methyl there. 3, 3, 6, 1, 2, 3, 4, 5, 6. Up or down doesn't matter, because we can rotate around single bonds. So we've taken care of the longest chain,
Dumbass. Not 3. H.
and there's the roots.
6.
All we have to do now is put H's at the end of every letter, and then we're done. So that's easier than the naming a drawing, okay? And notice the last 2 questions on the written response are exactly that. Draw from names, name from drawing. And there's a few in each of those, okay? We will get back to these soon. Now that I'm still gonna call it POS computer is running, let's return to the book, and you'll see we're making a couple little errors. But I'm pretty sure I had a better organic chem teaching or teachers. Right, organic chem teachers are actually more famous, to be honest. Seriously. But they were there.
Easy.
Yeah. It's pretty lucky. I didn't know that until I got in the guy's class, and then everybody says, "Well, you're lucky to get him." I go, "What? I don't know. That was the only one I had room for." Anyway,
That's aura.
2 in particular, Dr. Martin Cowie and Dr. Hooz, H-O-O-Z. He was often called away to present at international conferences.
I guess.
So let's go down to structural isomers. Carbon's properties use all 4 of its valence electrons to deplete its octet. Ability to form rings, chains of any length or any complexity, all of those things coupled together result in this, the phenomenon of isomers, okay? One type of isomer are called structural isomers. What are isomers? Well, they're different compounds with the same chemical formula. So, pentane and methylbutane, not 2-methylbutane, methylbutane, both have the same formula, C5H12. But if something's pentane, that means 5 carbons in a chain, C5H12. CnH2n plus 2. If the formula of a hydrocarbon is CnH2n plus 2, all it means is there's no multiple bonds between the carbons and there's no rings. All right? Just because, though, it's C5H12 doesn't mean that the 5 carbons are in a row. There's 2 other ways of connecting 5 carbons and 12 hydrogens together. This is the simplest way, a 5-carbon chain. But if we take a 4-carbon chain, we put a methyl here, it's called methylbutane, not 2-methylbutane. Why not 2? Because that can't be anywhere other than carbon 2 and it still be butane. It can't be here because that makes it pentane. It can't be there because it makes it pentane. And here are the same. They're both the second carbon. So when you say the word methylbutane, that is an unambiguous recipe for a molecule. There's only one place to put a methyl on a 4-carbon chain. Putting it there is the same as putting it there. You can't put it on carbon 1 or 4 because now it's pentane. It's still C5H12, but because the connectivity of the atoms are different, we call it a structural isomer. Here, the longest chain is 5. Here's the longest chain is 4. What about the longest chain of 3? Could you do that? Well, I'm glad you asked. Yes, you can. And if you do that, we have the 3rd structural isomer for C5H12. And we saw that in a worksheet. This is dimethylpropane, not 2,2-dimethylpropane. Meg. Just dimethylpropane. There's no other way to put 2 methyls on a propane than put them in the middle carbon. Okay. It should make sense that as the number of carbons increase, so do the number of ways they can be connected together. But they don't increase linearly, they increase exponentially. So notice all of these are CnH2n plus 2. You gotta go?
Yeah.
Go. C20 has more than 300,000 structural isomers, all different molecules with different properties. But the formula is exactly the same. Okay? Now, a lot of the molecules that exist in real life have carbons much more than 20. And then you get into isomers really in the billions. We can't and don't have the time to go into how there could be so many. Suffice it to say that there are. And that's really, the phenomenon of isomerism is really the biggest reason there are so many carbon compounds. What is a molecular formula for an alkane that has 12 carbons? If it ends in ANE, then it's got to be CnH2n plus 2. It's got to be C12H26. It doesn't have to be 12 carbons in a row, and there's a whole bunch of ways to put 12 carbons together. Only one of them would have them in a row. We didn't go into naming 12. That would be called dodecane, but you don't have to know that. Why is simply knowing the molecular formula, I would fix this, of most alkanes, not enough to draw a structural formula? For the first 3, it is. CH4 can only be built one way, methane. C2H6, ethane. C3H8 propane. No other way to build those first three. But as soon as you go to C4H10, I can have butane, or I can have methylpropane. But the first three, the formula is unambiguous. So that's why I said most. I will never ask you to draw condensed structural formulas. If you do that, you're gonna overbond the carbons. So, draw structural formulas for 3 of the structural isomers of C7H16. When you're sketching out isomers and thinking if they're different, if you know, see that CnH2n plus 2, no double bonds, no rings. So forget the hydrogens. They'll take care of themselves. Just focus on the carbon. So, 1, 2, 3, 4, 5, 6, 7. And if you want to draw all the lines in, you could, but trust me, you'll be there. Now that's 7 in a row, duh. That's one isomer. But what if we had the longest chain of 6? So let's put a CH3 here. That wouldn't be heptane anymore, would it? What would that be called? All those lines end in hydrogen. This is a methyl group, right? Which carbon is it on? 2. 2-methylhexane. The number's there because you need it. We could also have 3-methylhexane. Down or up doesn't matter. We can't have 4-methylhexane because that's just 3 looked at from the other way. That's a chain of 6. What about a chain of 5? Well, that's 2,2-dimethylpentane. That's 2,3-dimethylpentane. That's 3,3-dimethylpentane. There's no 3,4 because that's just 2,3. And as long as we're on that middle carbon, that's 3-ethylpentane. Get the idea? Yeah. So there's, asking for 3 is kind of softball. It's easy to get 3. But she's introducing the idea of different structures from the same formula. And then name them. Nothing to it. So far, so good? Okay. The next class of hydrocarbons isn't the next page here. It's 2 pages hence. So we'll talk about aromatics in a while. Now we're going to talk about what happens when carbon forms rings. The smallest alkane has 1 carbon and then 2 carbons. Could you have a ring with 1 carbon? No. Could you have a ring with 2? No. The fewest carbons required to make a ring has to be 3. So let's say we started with a 3-carbon alkane. You guys know that that's called propane, correct? But if I wanted to make that a ring, in other words, if I wanted to stick this carbon to this carbon, then the only way to put that carbon on this carbon is take away these hydrogens, right? So the formula for a cycloalkane, it still ends in -ane, which means every carbon is still stuck to 4 other atoms. But it's not CnH2n plus 2, it's CnH2n. So if I put that in a ring, a hydrogen on each of what we call the peripheral terminal carbons has to be removed. So I could draw this. And that's easy enough to draw, but it does add some complexity. So let's try to do that. Here's 3 carbon carbon in a row. So that's propane. I'm gonna connect this carbon to this one. So I gotta take two hydrogens away. So notice that isn't CnH2n plus 2, it's C3H6, right? And notice these fat ones, they're fat because they're not meant to bend. And if I try to make a 3-carbon chain ring from this, I can't really bend them properly. I have to use these sticks. Now, why would it be so hard to bend those straight ones into a ring? Well, you would agree that this should be an equilateral triangle, right? Look at each carbon. How many atoms is it stuck to? 1, 2, 3, 4. So every carbon is an AX4 center. What are the bond angles, ideal bond angles around AX4? What are the bond angles around a tetrahedron? Think of the balloons. 109.5. What do the interior angles in an equilateral triangle add to? Anybody know any geometry? Did you have any geometry in your youth? 180. The interior angles, not just in an equilateral, but any triangle, add to 180. Which means each of these bond angles have to be what?
60.
Can you calculate?
60.
60. Each of these bond angles has to be 60 degrees. That's 49.5 degrees smaller than what electrons prefer. In other words, they're way too close together. And that's why the only way to build a ring that small is use sticks that bend. 60, 60, 60. That means this is a very reactive molecule because we're packing a whole bunch of electron density into really small angles. Okay? We don't call that propane. It ends in propane. All we do is put a prefix cyclo in front of it. Cyclopropane. Notice that it's a flat molecule. Even though all of the centers are AX4. Notice something else. In a chain, remember I said it didn't matter whether you added groups up or down on a chain because you can freely rotate a chain. You can't on a ring. Which means if you're going to add things to these carbons, whether they're on the same side of the plane of the ring or on opposite sides, are different molecules. And we don't call those structural isomers because the same atoms could be on the same atoms. So let's go to methyl, for example. And Meg doesn't do this, I'm not surprised. If you put one thing on there, you don't have to number it, because putting it here is the same as putting it here or here. So that would just be methyl cyclopropane. And we'll go into naming these in a minute. But let's say I had 2 methyls. I have a choice. A couple of choices. I could put the 2 methyls on the same carbon in the ring. Now I do need a number. Now it would be 1,1-dimethyl cyclopropane. I could also put it on this carbon. And this carbon is the same as that carbon. But I can't just call it 1,2-dimethyl. Because the methyls are on opposite sides, opposite planes of that ring. And there's no way to get them on the same side by twisting any of the bonds. I gotta break bonds. So this is 1,2-dimethyl cyclopropane. But that's not enough, because so is this. This is also 1,2-dimethyl cyclopropane. And yet the same atoms are stuck to the same atoms. So it's not a structural isomer. We're going to learn next class that this is called a geometric isomer, where the connectivities are the same, but the orientations in space aren't. So we use what we call stereo prefixes. If two things are on the same side of a ring, or, as we're gonna see, a double bond, which is coming up, we use a prefix cis, cis, meaning same. So this would be cis 1,2-dimethylcyclopropane. And that's not the same as this. When they're on opposite sides of a ring or a double bond, the prefix we use is trans. That's trans 1,2-dimethylcyclopropane, and they're not the same molecule, even though the same atoms are stuck to the same atoms. They're both 1,2-dimethyl, but their orientation in space is different. Meg doesn't do that at all for cycloalkanes, and I know why. She's trying to stay simple. The reason I'm doing it is because when you guys do the lab and try to find, for example, all the isomers of C6H12, there will be a whole bunch like this, where the groups are on opposite sides or the same side of a ring. And it gets even better than that. Because if you took the mirror image of this thing and built it, it's not the same molecule.